Right. Okay, Venus.
Yes, yeah. Yeah, so thank you so much everyone for joining us. Good afternoon, evening, morning, different time zones. Today we have the pleasure of having Dr. Matti Heikenheimo. He did his PhD in Jyväskylä, in a town basically in the well, southish of Finland, where there's more snow than Helsinki. He's done a couple of postdocs in Canada, in Estonia, and then in Finland. And I've had the pleasure of working with him on a couple of projects. But the talk that he's going to give us today is not on the stuff that I know very well. It is basically on directional detection of dark matter. And yeah, I'll give the virtual floor to you, Matti.
Okay, thank you. Yes, let me share. So I hope you see this.
Yes, we do. Yes.
And all right. So yes. So my plan is to talk about direct detection of dark matter and specifically some topics that we have been working on now for a couple of years regarding condensed matter effects for low energy experiments in this field. So I am a theorist by training. Now for the past couple of years, I have been kind of approaching this experimental side more, but I am by no means an expert on these experiments, on the experimental details. But yeah, let's see what we can uncover here. And as I understand, most of the audience is probably theorists, so maybe I can use this kind of to try to present kind of an introduction to these kind of experiments, and then yeah, let's see. And indeed, if you have any questions during the talk, just feel free to ask. Okay, so I will give some introduction to the general idea of dark matter first, and then to these direct detection experiments, and then I'll go through a couple of use cases for these material science effects that we have been studying. The first one is this kind of modulation experiments. Then I'll talk about the solar neutrino background for these experiments and how this can be used to maybe separate the signal from the background, and then a last case regarding this kind of change in the observed energy spectrum of these experiments due to the effects. Okay, so first, dark matter is a part of our standard model of cosmology, but it's not a part of the standard model of particle physics. So it is so far believed to be some kind of an unknown particle that we need to include into the standard model, or we need to extend the standard model to include the dark matter particle. There are many evidence for the existence of dark matter, starting from this maybe most famous example, the galactic rotation curves and velocity dispersions. So we look at individual galaxies and we look at how fast the stars and the gas rotates around the center, or in the case of elliptical galaxies, how fast or what is the velocity dispersion of the stars in different regions of the galaxy. And by Newtonian mechanics, this should be given by the potential, by the gravitational potential of the system. And now when we look at the visible matter in the galaxy, we see the stars and we see the hydrogen gas. We can estimate from the intensity of light and the radiation coming from the galaxy that how much visible matter there is, so how much it weighs, how deep should the gravitational potential well be, and then we get this kind of a prediction for the curve. So as a distance from the center of the galaxy, this should be the rotational velocity. But what we observe instead is this curve. So it means the stuff is moving faster, which means that it must inhabit a deeper gravitational potential for the system to be stable. Otherwise, the stars and the gas moving with this velocity should be expelled from the system if the potential was only generated by the visible matter that we see. So this implies that there is some invisible or dark matter inside the galaxy and surrounding the galaxy that keeps that explains this gravitational well. Then we have gravitational lensing observations from mainly from galaxy clusters. So gravitational lensing is of course this effect by from general relativity, the bending of light. So when we have an object, a heavy object that curves the geodesics around it. So when we have a light source behind such an object, then we see a distorted image of this light source, or we might even see multiple images of it, and then reconstructing using these distorted images, we can try to reconstruct the gravitational potential in between. And this also implies that there seems to be more matter in galaxy clusters than the visible matter. And one very striking example of this is this so-called bullet cluster, which is not a cluster in its kind of equilibrium state, but a collision or beginning of a merger between two galaxy clusters. So a larger galaxy cluster here and a smaller one here that has passed through the larger one. And what we see in the color here is the X-ray emission intensity from this system. And X-ray is emitted by the hydrogen gas. And actually most of the visible matter in the galaxy clusters is in the form of this kind of sparse X-ray emitting hydrogen gas. It is not in the stars, but in this sparse gas that is mainly located between the galaxies. So these are galaxy clusters, both consisting of multiple galaxies, and most of the visible matter in these systems is actually in the gas between the galaxies. And that gas, when it passes through another kind of a cloud of gas or plasma, it interacts and it gets slowed down and heated up, and we can see this kind of a shock front appearing in this smaller of the gas clouds or the galaxy clusters. It's called intracluster medium, this X-ray emitting gas. And so the name bullet cluster comes from this bullet-like shape. It has, like the bullet has shot through the other gas and it has slowed down. Whereas, which is not shown in the plot here or in this figure, are the visible stars. They do not collide. So in the galaxy clusters, there are galaxies here and there, but most of it is this sparse gas between the galaxies. It is kind of rare for two galaxies to collide or to merge in such a system. Mostly the galaxies that just pass through. So the galaxies and the stars in this sense are collisionless, whereas the hydrogen is collisional. And the stars are mainly located here and here. And now when we look at the gravitational potential, which is shown by the green curves here, so these are from the reconstruction of the gravitational lensing. Now the gravitational potential, the maxima of the gravitational potential seem to reside with the stars. And we know that most of the mass of the system, of the visible mass, is in this hydrogen gas. So if there was only visible matter in the system, the gravitational potential should follow mainly these hydrogen clouds, not the stars. But it seems to follow the stars, so it means that most of the mass in the system is also collisionless like the stars, because the stars are dense and almost like point-like objects in this scale. They go through or past each other. But now it appears that also most of the mass of this system behaves similarly to the stars and just passes through the other system. So it means that this dark matter does not significantly interact with the hydrogen gas, but it
sorry,
also...
Matthew,
yes.
if I might interrupt. The reason you don't see the stars presumably is because this is an X-ray.
Exactly. So this is an image in X-ray, and then overlaid are the contours of the gravitational lensing. So there are images from this system that also show the stars, but there is a lot of stars in the foreground. So if you just show the Hubble image, you don't really by eye see the actual clusters in light, because this system is kind of far away and there are a lot of stars in the foreground. So the image, you just have to take my word for this, that the image, when you actually remove the foreground stars and just look at where the galaxies belonging to this system are. They are here more or less close to so the peak of the luminosity is kind of close to the peak of the gravitational belt, but yeah, they are. It's not shown here in this plot. Yeah. So indeed, this color plot is just in X-ray, and the visible stars, they mostly emit in visible light, of course. So they do not show up in the X-ray chart. Yeah. Right. So the conclusion that we indeed can draw from here is that that it is a kind of a separate type of matter, because most of the visible matter is here, and this matter that gives rise to the gravitational potential well has been temporarily separated from the visible matter. So this kind of strongly is kind of a strong evidence for this kind of existence indeed of two types of matter, where this dark type is collisionless also amongst itself and collisionless with the visible matter. Right, then there is evidence from the cosmic microwave background, specifically when you look at the power spectrum. So this is the 2-point correlation function between the temperature map of the cosmic microwave background. So if you have a denser point at some point, this function here shows the probability kind of finding an overdensity at the given distance of that point. And we know that there are these preferred scales where this probability should be higher, and these are given by the so-called acoustic oscillations. So in the early universe, when the matter begins to so the theory is that we have inflation, and inflation leaves us with almost a flat universe, but with some fluctuations given by quantum fluctuations of the inflaton field. So those fluctuations appear as fluctuations in the energy density of the universe. They begin by the effect of gravity to increase. So the gravity tends to increase the overdensities and make the underdensities more underdense, of course, because the overdensities attract more matter. But visible matter has this counter effect to this. As it collapses to smaller and smaller regions, it heats up and starts to emit more and more radiation, and this radiation pushes back against the hydrogen atoms coming in. So visible matter begins to oscillate in these overdensities, and this kind of oscillatory scale that we see here are come from this kind of oscillation. So this largest peak is the first maximum when the shell, the outer shell of the first maximum given by the speed of sound in this primordial plasma. Now, dark matter, since it is collisionless, as we just saw in the previous figure, does not exhibit this oscillatory behavior, but just collapses. So depending on how much dark matter and how much visible matter you have, they of course both inhibit the same gravitational belts. So this changes the relative amplitude of these peaks. This is of course not the you have to do a careful analysis of the situation to compute what you actually then expect to see in a given model of the universe, but indeed this has been done with great accuracy, and indeed, as you can see, the points, the error bars on these points, when you go towards large and multiple moments, the error bars become invisible. So this is a very precise measurement, and the points lie exactly on the line, which is a prediction from the current best fit Lambda Cdm model. So this is a very good measurement also of the relative abundances of dark matter and visible matter, and the rest is then has to be dark energy, which is the dominant contribution in the energy budget. But so this is the most precise measurement of the amount of dark matter, and it is roughly 5 times as abundant as visible matter in the universe.
Sorry, Matthew,
Yes.
The reason the error bars on the left-hand side are really large, it's because we don't have, it's just the one early universe, right? Exactly
right. So the axis on here is on the bottom axis we see the angular size, and on the top the multiple moment I mean, which are it's the same axis but in different units. So indeed, the first to the left, you have larger and larger scales. So of course, if you divide the sky into two halves, then of course, I mean, there is a statistical fluctuation in looking at the correlation between this half and this half. So you, since you only have one repetition of the experiment, you cannot get, so it is limited by statistical uncertainty. Whereas towards the higher scales, of course, you have more statistics.
So from this plot, I shouldn't say our theories for the early universe behavior are not very accurate. I mean, for other reasons, I know that we don't know what happened in the early universe, but from the basically experimental points not landing exactly on the green line, you wouldn't say the theory Lambda Cdm is not a good theory in the early universe.
No, I mean, so this seems to fit very well. I mean, I would say that indeed. So this fluctuation here in the leftmost part is just the statistical fluctuation. So I mean, this is expected just from the statistics. So indeed, yeah, I mean, so there are of course some problems with the Lambda Cdm model, like for example, when you compare the Hubble rate that you extract from this figure and compare it to the one that you measure from supernovas, they don't seem to agree. So there are some issues indeed, but for the purpose of just measuring the amount of dark matter, this seems to be a very good measurement. Now, of course, if you have to go and change the Lambda Cdm model, it might be that you also have to change the amount of dark matter. So by no means this Planck measurement is necessarily the final word on the subject, but indeed, in the context of a given model for the universe, such as the Lambda Cdm model, this gives a very precise measurement of the amount of dark matter.
Can I ask a question?
Yes.
What would the shape of that curve be if you excluded dark matter, if there wasn't any dark matter?
I think the second peak would be much higher and the third peak would be lower. This is my quick guess of this, but I am not completely sure. There are actually some nice tools you can search for online, like CMB plotter or something like this, where you can play with you can dial the amount of dark matter or dark energy, and then you see how the peaks move. So
okay,
and so from the top of my head, I can't exactly say.
Okay, and what about dark energy? None is included there?
Here is, so this assumes the standard Lambda Cdm model. So this assumes the 70% or so of the energy in dark energy here. Yes.
Thanks.
Okay, right. And then the last kind of evidence for dark matter that I want to point out here is just the observation of the galactic and the larger scale structure that we see in the universe. So as the story goes, indeed, we start from this very kind of evenly distributed plasma, which then begins to collapse and form structure under gravity. So this is these figures are from you just make a cube of a universe and just allow it to evolve under this simulation. I believe is just under Newtonian gravity and containing only dark matter. So there is nothing else in this simulation but dark matter, and you just follow how the dark matter, if you start it with 10 to minus 5 over and under density, so the relative under densities or over densities are of the order of 10 to minus 5 to the average density, which is what we kind of see from the CMB, and then we allow it to evolve. This is what we get. You get this kind of a network of these filaments, and in the where the filaments are entangled with each other, there are these clumps which correspond to the galaxy clusters that we see today.
And presumably this is the evolution of dust. You treat it as
exactly.
Dust, pressureless. Yeah.
Exactly. So these are collisionless point particles that have basically zero velocity and zero pressure. So yes. So the so-called CDM, cold dark matter component, and this is what it kind of forms, and this matches very well what we see in the universe up to this kind of scale of the Milky Way size galaxies. When we look at structures smaller than the Milky Way, then there actually starts to be discrepancies from this picture in what we see. And this is because at those scales, what baryons do, or baryons, by baryons in astrophysics, I mean hydrogen gas, basically what hydrogen does, forming stars and then building supernovas that violently explode and move the gas around. Those effects start to modify the structure at the scales somewhat smaller than our own galaxy. So these kind of simulations that only contain dark matter give a good picture on very large scales, but on smaller scales, you have to include the effects of visible matter. But indeed, if we only had visible matter that has pressure and radiates and so on, this process of structure formation would be quite different, and it is hard to reconcile it with the picture that we kind of see as an initial state in the CMB. So this is another kind of evidence for dark matter. So all of these evidence or hints for the existence of dark matter, they are kind of from different scales, from the galactic scale to the scale of the whole visible universe in the CMB, and kind of contain different dynamics, the mergers of these clusters kind of that we see kind of in real time in the bullet cluster, or then we can try to reconstruct this history, how the structure was formed. So there are different evidences that I would say a priori would not have to be explainable by a single answer, but they seem to be. So in this sense, the particle dark matter seems to be a very economical explanation for all these different pieces of evidence. But all of these are based on the gravitational interactions between dark matter particles themselves and between the dark matter and visible matter. So we don't have much information about the non-gravitational interactions of the dark matter. And of course, as particle physicists, we would be very interested in understanding if dark matter, first of all, is a particle, then what kind of a particle it is, how does it interact, kind of how do you put in the dark matter particle in the standard model, what kind of a thing it is. Now, of course, there is like a whole universe full of theories or models for dark matter, what it could be. And there is really not much limitation to what you can come up with. So what we would like to do is of course to get some observations, to see something, how it interacts, and then use this to kind of limit the model space to better understand what kind of a particle it is. Now, if the dark matter particle is a so-called WIMP or a thermal relic, then we have a bit better handle on how it behaves. So by thermal relic, we mean a particle that in the early universe is in thermal equilibrium with the standard model particles. So it interacts strongly enough with the standard model particles so that it reaches thermal equilibrium. So then you have a bath of particles that all are scattering off each other, so that every particle species has an equilibrium distribution. Then as the universe cools down and expands, the number densities of the particles become smaller and smaller, and at some point the particles no longer find each other, so the scattering stops. And then if they would follow the equilibrium density, then of course the number density of particles just goes down exponentially as a function of the temperature. But since they stop finding each other, they can no longer annihilate. So this is the so-called freeze out process, meaning that then you are left with an abundance of particles that is determined by the strength of this annihilation process. So the stronger the annihilation cross-section, the less particles you have, because they will be able to follow the equilibrium curve for longer time. Now, if this is the mechanism that sets the dark matter abundance, then it has a prediction for today. We should be able to see these annihilations, these same annihilations taking place today in the regions where dark matter is overdense, so such as the center of our galaxy. So this is so-called indirect detection, which I will not discuss in this talk, but this is like one of the connections. Now, of course, if there is this interaction between the dark matter and standard model particles, then we can try to also see the inverse process of this annihilation. So we can collide two visible sector particles, mainly protons at the LHC, and try to see the production of two dark matter particles, which we would see as missing energy and missing PT in the collider experiment, because presumably our detectors will not see the dark matter particle, but they will see whatever else is produced in that collision, and then you will see that there is an imbalance in the momentum. So something has escaped the detector. So far, this has not been seen. And then the third way of observing the same scattering diagram, which is now the topic of this talk, is so-called direct detection. So we are trying to see an initial state consisting of one dark matter particle and one standard model particle going to a final state of one dark matter and one standard model. So elastic scattering between dark matter and standard model, where we, of course, observe the standard model particle and see it getting a recoil from this collision with the dark matter particle. So this is the idea. So the direct detection experiment in all simplicity consists of some bulk of matter that we are watching very carefully, and that we have isolated from any radiation sources or whatever.
Before you go into this,
yes.
Do you have any limits on the cross-section?
Sure. So of course, I mean, this process itself, if we believe it is a beam, this of course gives us kind of a target cross-section for what the cross-section should be, so that the abundance is what we observe. This depends slightly on the dark matter mass, but anyway. So this is, okay, this is not actually shown here on the plot, but anyway, so there is a kind of a target number for this kind of thermal relics. And now from this indirect detection, assuming now of course, many of these limits always come with some kind of caveats. So for example, this indirect detection now, the limits slightly depend on what the annihilation product is. So for example, if the dark matter annihilates into two photons, or whether it annihilates into two neutrinos, then of course the limit will be different, because it is more easy for us to see the photons than it is to see the neutrinos. For anything annihilating into any charged particle, basically anything else than neutrinos, we have already limits from looking at our own galaxy and the dwarf galaxies surrounding us from this indirect detection that rule out this thermal relic cross-section for the dark matter up to something like 100 GeV of the dark matter mass. Now, the heavier the dark matter is, since we know how much dark matter there is, if the dark matter particle is heavier, then the number density of the dark matter particles is smaller, of course, because the overall mass we know. So the heavier the dark matter, the less dark matter particles there are, meaning that less annihilations will be taking place. So that's why all these limits kind of constrain the dark matter up to some mass typically, but not for heavier particles. And for this indirect detection, the limit is roughly of the order of 100 GeV or so.
Can it be massless? Can I ask, can the dark matter be massless?
No, it cannot be massless, because it has to be cold, in this sense that it forms structure. If it is massless or very light, it would have a large velocity, and specifically that, so it would be streaming and not collapsing into gravitationally bound objects. So there is a limit for the for so-called warm dark matter, that the dark matter mass has to be at least of the order of a few kilo electron volts. This is kind of the lower limit for this, again, for this kind of a thermal relic dark matter that was once in equilibrium with the standard model. Otherwise, it would be too fast to form the structures that we see.
So there's a limit on the axion mass, I mean, right?
Yes. So then if you have a particle like the axion, which is very, very light, then it is not a WIMP in this sense. It has not been produced with this mechanism. So it is not a thermal relic, but instead it was produced in some sort of a phase transition or something like this, which means that then the initial state of this particle is different. It is a very cold, I mean, it's more like a condensate like a classical field. It just turns out that the equation of motion, or the kind of the equations of state of this kind of a classical field with the chi-squared potential is basically the same as for cold dark matter. So that's why the axion looks like particle dark matter when you look at it at scales larger than the, let's say, the de Broglie wavelength of the axion. But for axion, all of these experiments are different. So this picture that I'm showing here that describes the scattering between the particles just holds for this kind of a WIMP or a thermal relic kind of dark matter particle that has a mass of at least of the order of kilo electron volts. These very light axion-like particles, you have to try to detect them with different mechanisms. So it's kind of a different world for those kind of dark matter particles, which certainly are also a possibility. But yeah, there are separate experiments then for those.
And then at the other extreme, can you put an upper limit? Could they be Earth's weight dark matter?
Yes, so there is some upper limit, of course, from, again, that kind of comes from the granularity. So if the dark matter would be, so I mean, in this case, you typically talk about like primordial black holes. So the dark matter could be primordial black holes. Although there are then many constraints for this from various sources. But yeah, I mean, obviously the mass then cannot be larger than some kind of, like, if we see a galaxy with let's say 1 million solar masses, then we know that the gravitational potential of that object is kind of smooth. So if the dark matter particle mass was 1,000 solar masses, then there would be only 1,000 of them making the halo, so it would already be kind of granular. So from this kind of arguments, we can say that there must be some upper limit. I don't know what the number is, but it's I mean, certainly very far away from this kind of particle physics.
It seems that the limit is very large if you're talking about.
Yes. So at least, yes, at least primordial black holes of the order of a solar mass, or even, I guess, a couple of orders of magnitude larger could be possible, but they are constrained from like micro lensing experiments. I think for this heavier part is the most relevant. So you would try to look at some object, some star, and then indeed, if dark matter would be this kind of very dense, big massive clumps, at some time some clump like this would move between you and the source of light, and that would give you a temporary lensing effect. So from these kind of constraints, I think the current situation is that not all of dark matter can be in this form. I believe almost all of the kind of the parameter range of these primordial black holes is constrained such that you cannot have all of dark matter in this form, but you could have, let's say, 1/2 or so. This is my rough understanding of the situation, but these kind of limits are also improving all the time. So there are many different kind of indirect ways to look for these kind of things, how they affect this micro lensing, or how they would affect yeah, I wonder what are well, for this kind of stellar mass objects, I think the micro lensing is the most relevant.
Can you ask, if they were primordial black holes, what is the signal?
Yes, so if they are very heavy, then I think the signal would be this kind of just that you see this kind of heavy, I mean, and it doesn't have to be primordial black hole, it could be any so-called macho. So if it's a very heavy stellar mass object, then you see it as a point lens, sometimes disturbing the light that comes to you from some objects that you can carefully follow. But for smaller than that, I don't know. There are many different limits for different kinds of mass ranges for the primordial black holes. But unfortunately, I from the top of my head, I don't really know which are the current most relevant experiments looking for those.
But they would have horizons. What I'm asking is, they would have horizons, and there will be black hole collision and annihilations. So this
yes. so the mergers, of course, yes. I mean, the mergers of the primordial black holes, again, you should see them. I think currently with the, the amount of mergers that we have seen with LIGO is still compatible more or less with having dark matter in this form. The precise rate of these mergers is not easy to compute, of course, because you would have to know how often they kind of form these gravitationally bound pairs that then will merge, and this depends a lot on the initial condition, on the distribution of the black holes. But yes, indeed. So the merger signal is one that you can use to constrain it, or you could use to possibly observe it. But I think so far, the observations with LIGO are compatible with all the black holes that they have observed being stellar remnants, but it would be also compatible with there being some primordial black holes. So we cannot really say yet.
I have one more small question. In quantum field theory, a field need not have any particle at all. It can contribute energy, but there may not be any particle associated with it. Why is this possibility not examined? It is well known. This fact is well known.
So I guess this. I'm not really sure how. For the this kind of astrophysics situation, I think the relevant quantity to understand is this kind of an equation of state. So basically the relation between energy density and pressure. And this has to be to a good approximation equal to this kind of, so basically zero pressure. And for the axion field, for example, this works. So the axion, even though there is an axion particle, but I think the axion dark matter is more like a field. So I guess this kind of a solution is indeed possible, but yeah, indeed, then you cannot search for it with this kind of a scattering experiment. You must try to see the interaction of the field with some standard model field. Like for example, axions, you try to look at how the axion field interferes with the electromagnetic field in some sort of microwave cavities or these kind of experiments. So if this is the solution, then of course you have to understand how the field interacts with some visible field and then try to build an experiment based on that. Okay, indeed. So of course, yeah, the landscape for the dark matter models is very, very wide, and these kind of direct detection experiments that I'm describing, they only cover a part of that landscape. So they can only touch this part where the dark matter particle is kind of not too far away from the standard model particles, let's say. So it is a particle with the mass kind of in the same ballpark that the known particles that we have in the standard model. If it is too heavy, then the number density of these objects will be too small for these scattering processes. They would be too rare so that we cannot see them. And if it is too light, then it cannot deposit enough energy in our experiment so that we could see it. So there is a window that can be probed with these kind of experiments. And of course, we have no a priori reason to somehow say that the dark matter must be in this range. So in this sense, there is no guaranteed success in building these experiments. But of course, you have to try, right? So with this in mind, we come to the kind of a basic principle of these direct detection experiments. So you have some bulk of matter that you watch carefully, and you try to observe this dark matter particle hitting it and depositing some amount of energy in your bulk of matter that you are observing. So you are trying to see the energy coming from nothing to your bulk of matter. Now, what this matter is, there are various experiments. I'll mention them in the next slide, but for example, in this picture, there is a liquid noble gas in a tank, which is surrounded by photomultiplier tubes. So then you would have a scattering event taking place, which excites some atoms, and as they de-excite, they emit so-called scintillation light, and then your photomultiplier tubes observe this scintillation light, and this is your signal. So this is what you try to observe. Or here in another experiment, you put in an electric field on top of the tank. So now if there is an ionization event, then the electrons will drift in the field, and then you will as there is some gas phase on top of the liquid phase. So once the electrons reach the gas phase, the electric field will they accelerate them in the gas so that they will hit many more atoms in the gas, and then you observe the light that comes from this kind of a burst. So there are many techniques based on observing and somehow amplifying the energy that is deposited in the matter. But the basic principle in all of these experiments is the same, that you watch some bulk of matter and you try to see these kind of scattering events taking place. Now the rate of these events depends on, of course, the local dark matter density. So this is the energy density stored in dark matter in our local surrounding, divided by the dark matter particle mass. So of course, rho divided by m is the number density of dark matter particles. And this is why if this mass is very heavy, then the rate is very small. So you see the event rate is directly or is inversely proportional to the dark matter mass, just because the number density scales like 1/m. Then it depends on the we can divide this dependence of the event rate into the dependence on the astrophysics, let's say, parameterized here by this function f of v. So this is the velocity distribution of dark matter, giving the probability to find a dark matter particle with the given velocity in our lab frame. So this depends on what is the distribution of dark matter particles in our local surroundings, how are they moving with respect to us in the galaxy. And then the other part is the d sigma dE, which is the differential cross-section. So this is kind of the particle physics input. So depending on what kind of a particle you have, if you have a Lagrangian for your model of dark matter, then you can compute this cross-section, scattering cross-section from the nucleus d sigma dE. And these two together give you the expected event rate for your model. Okay, now you have multiple experiments like this. This is a partial list of all the experiments that are running currently or have been conducted using different elements as the target material. There are solid state targets like germanium or sodium iodine, and then there are liquid noble gas experiments like xenon or argon, or there are even some gaseous experiments like bubble chambers. And you see the target mass varies from portions of a gram to a couple of tons. And the largest of these experiments are the ones using argon or xenon, kind of like this one here. This is from this xenon 1 ton experiment. That is currently right now the xenon n ton, which is even slightly larger than this one, is collecting data. So these are the largest experiments using this liquid noble gas, and they give the most constraining limits currently, which is shown here. So when we give a limit to the scattering cross section, this of course now includes assumptions both of the velocity distribution and of the scattering operator, as I described before. So the velocity distribution, we assume a certain so-called standard halo model, which means basically a thermal equilibrium distribution, like a Maxwell-Boltzmann distribution for the velocities of the dark matter particle in the galactic rest frame. And then we know how the Earth moves in the galactic rest frame. So we just make a coordinate transform to the laboratory frame. For the scattering cross-section, they are typically presented for this simplest possible so-called spin-independent cross-section, where d sigma dE is given by this kind of dark matter nucleon cross-section. So this would be the scattering cross-section between a dark matter particle and a neutron, or a dark matter particle and a proton. And in this spin independent assumption means that they are the same. So you assume that the dark matter particle has the same cross-section with the neutron and the proton. And then the scattering from a nucleus is just given by this number times a squared, where a is the mass number of the nucleus, times a form factor that describes the kind of loss of coherence when you scatter from a finite size nucleus. So this is a function of energy. And then there is just some kinematic factor here. So then basically this is this sigma chi n is the quantity that you constrain. So this would be kind of your particle physics quantity. Now, of course, if your theory predicts that the dark matter particle, for example, somehow couples to the electromagnetic interactions, then of course it would not couple equally to neutron and the proton. So then you must use a different, then this formula is not valid. But for the simplest kind of theory that you just, let's, for example, say you couple to quarks with this kind of a 4 fermion effective interaction, then you get this kind of operator. And this is kind of the standard for presenting these limits. You can of course translate them then into if you have a more complicated theory, you can translate the limit to those, but then you must compute, of course, for different materials, different limits, because if the coupling depends on, for example, on the number of neutrons and protons, then for each target element you must individually compute the rates. So this is nice simplification in this sense that it allows you to compare these different experiments that use different target materials, because it only depends on the mass number like this. Which of course we don't know if it is the case or not, but this is the simplest scenario. All right. So what we see here is that these limits are kind of have the same slope, which is just the 1/m slope. So this slope just comes from the number density of the dark matter particle scaling as 1/m. So you see here in the x-axis we have the dark matter particle mass, and then each of the experiments has kind of a low energy cutoff where the sensitivity turns up. So the region above the line is always ruled out. So the experiment doesn't see an event rate above some background that it assumes, and then it can rule out a cross section larger than a given value. But they all turn up here at some mass, roughly of the order of 10 GeV or so, depending on the experiment. And this is because here in this formula, we have this integral over the velocity distribution of the dark matter from some minimum velocity, which is given by the kinematical constraint to excite the recoil of the energy ER. Now each experiment has some lower limit on the energy that it can observe. So of course you can only constrain dRdE above that threshold energy that your experiment is able to see. For example, this xenon, if the recoil is not energetic enough to excite the atom so that it would give out luminescent signal, then of course you cannot see it. So there is some energy lower energy required for the experiment to see the signal, and then this implies a lower limit here on this integral. I mean, you put in the lower ER that you are able to see, and then this V min again depends on the mass of the dark matter particle. It's hidden here in this is so-called reduced mass of the dark matter nucleus system. But if the dark matter is lighter than the nucleus, then this is basically just given by the dark matter mass. So this V min roughly for light dark matter, it scales roughly like 1/m chi, which means that if the dark matter is very light, then V min becomes large, and at some point it becomes larger than the escape velocity of the dark matter particles from the gravitational well of the galaxy, and we expect that dark matter particles with velocities higher than that escape velocity, they don't exist because they have enough velocity to kind of evaporate from the galactic halo. So that's why this integral goes to 0 for light dark matter. So that's why each of the experiment has a different target nucleus. So of course, I mean, there's also the dependence on the nuclear mass. So that's why they have this. And of course, every experiment has a different experimental technique to observe the signal that comes. So they might have different energy threshold that they observe. But anyway, each of them has some kind of a lower limit for the dark matter mass that they can see. And now, so as you can see, there is kind of empty room here on the left where we have not probed yet cross sections for the dark matter that have been probed for heavier dark matter. So there is currently a lot of effort to build experiments with lower energy thresholds so that you could probe dark matter with smaller masses so that you can kind of cover this range here. And this is mainly where I will now focus to look at experiments that have been able to build low thresholds, and then what are the new things that we have to take into account in that range. The neutrino floor that we saw here in the bottom comes from the neutrino background. So of course, a neutrino hitting a nucleus in your target looks kind of exactly like a dark matter particle hitting the nucleus. The neutrino comes from nowhere, or you don't see it coming, and then it just hits your nucleus. So you get an energy deposition in the target. And even the expected event rate, so this is a spectrum DEDR that you can predict for your dark matter model. It has a kind of typical spectrum like this, or like this, depending on the dark matter mass. The recoil spectrum from the neutrinos looks very much like the recoil spectrum that you typically predict from dark matter. So even clearly, very carefully looking at the spectrum, it's hard to separate the dark matter signal from the neutrino background if your experiment is sensitive enough to see these solar and cosmic neutrinos. The current experiments are not yet sensitive enough. As you see, the current experimental limits are still above this neutrino floor. But once you increase the size of your experiments enough, there will be this irreducible background that that kind of limits the range that can be tested with this technique. All right, to circumvent this solar neutrino background, we can try to use the timing information. So in addition to the energy spectrum that looks similar to the neutrinos and the dark matter, we can try to use the timing information. And this idea comes from the fact that the Earth, as it's moving around the sun, and the sun is moving with respect to the galactic rest frame, where we assume the dark matter particles to have this Boltzmann distribution. Then effectively the dark matter velocity distribution in the lab frame becomes a function of time, because the lab velocity is a function of time due to the motion of the Earth with respect to the sun. These are roughly the scales. So the velocity of the sun with respect to the galactic rest frame is of the order of 200 kilometers per second. And then our motion with respect to the sun is of the order of tens of kilometers per second. So roughly 10% or so of the 15% of the variation in the galactic, I mean in the lab velocity with respect to the total velocity that we are moving with respect to the galactic rest frame. Now, this is not exactly the plane where Earth revolves around the sun is tilted with respect to the galactic plane. So these don't directly add. You have to add the vectors, and so the variation is not actually 15%, but you expect in the event rate roughly order of 5% modulation between summer and winter in these experiments. And there is actually one experiment that claims to see this kind of a modulation in the event rate that it observes, this Dama-Libra experiment. This has been measuring for more than 20 years already, and they claim to see this kind of modulation. But the problem with this experiment is that it is hard to fit this observation with any model that would not be ruled out by the other experiments not seeing anything. So this situation is kind of puzzling at the moment, but people usually don't consider this as evidence for dark matter because there are many other experiments that don't see this. So this is currently kind of a puzzling situation, but we would like to have more experiments observing this until we kind of, well, can clarify this situation. Anyway, this annual modulation is one idea that has been around for a while. Now, another idea is to use the daily motion that, of course, comes from the rotation of the Earth around its axis. Now, the velocity, if you have a lab on the surface of Earth, the velocity related to this rotation of the Earth is very small, of course, compared to the velocity of the Earth moving around the sun. So this doesn't give a significant effect. But of course, it changes the direction of this dark matter wind by a large amount every day as the Earth rotates. Now, if you have an isotropic target like the liquid xenon, then there is no effect. But if you have a solid state target, then in principle there is a preferred frame, of course, because if you have a crystal, then the crystal has some crystal structure, and not every direction in the crystal looks the same. So there, in principle, your target is then anisotropic, and it is possible that the scattering rate would then be different depending on the direction of the incoming dark matter particles. And this is what we are trying to see. Now, this becomes important when the scattering energy is of the order of the binding energies of the particles of the nuclei in their lattice sites. So if you have a very high energy collision with, let's say, a germanium atom in a germanium crystal, then it is to a good approximation equal to the situation that you would just have a free germanium atom being hit. But if the scattering event, if the energy deposited to the germanium atom is of the same order as the binding energy of that atom to its nuclear, to its lattice site in the crystal, then you cannot no longer approximate the situation as a free atom being hit, but you must take into account the surrounding lattice structure. So these formulas that I showed before for the nuclear scattering rate, they were all for this kind of 2-to-2 scattering between a free nucleus and a dark matter particle. But now, as we try to move towards smaller and smaller recoil energies to be able to probe lighter and lighter dark matter particles, we must start to worry about this kind of solid state effects that the particle is not in isolation but is a part of a crystal. Now, the first use case for this that we have considered here is this kind of an experiment using indeed germanium, where you have a voltage over your germanium crystal, and you try to see the ionization that happens when you hit an atom in the crystal. And now this device, this has already been built or prototyped. It is sensitive enough to see a creation of a single electron hole pair. So if you create a high energy scattering that ionizes a lot of atoms, then again you don't have to worry about this. But if you, now that your experiment is sensitive to a creation of a single electron hole pair, then you must start to worry about this lattice structure. And here we are using a conjecture that is not yet fully tested, but seems some density functional theory calculations have been done to kind of support this idea that the threshold for creating an ionization event, if you hit a nucleus in the crystal, would be, if not equal, at least correlated with the threshold of creating a lattice defect. And this creation of lattice defect is a problem that is well studied using this kind of molecular dynamic simulations, where you just study the nuclei using classical potential between the nuclei. So these kind of simulations are feasible. The simulations that also try to model the electronic structure in the crystal are much more complicated. They must be done using this time-dependent density functional theory, and very kind of detailed simulations like this have not yet been performed. So this is not a fully solid statement, yes, but seems like a plausible conjecture that there is a connection between this creation of a lattice defect and an ionization. And if this indeed is the case, then what we see here in this plot is from molecular dynamic simulations looking at the yes.
Sorry, Matty, doesn't that have to depend rather strongly on the material that you're using?
Certainly. This depends very strongly on the material, yes. So I will come to different materials in the end, yes. So we started looking at germanium because indeed one of the many of these experiments use germanium, and these experiments that have very low thresholds, many of them use germanium. So this was something that we wanted to start with, but indeed we have also looked into different materials. So here you see in this figure in color code the threshold energy for creating this kind of defect, a lattice defect in the crystal. So if you hit an atom in a given direction, how much energy must you give it for the atom to move away from its lattice site and to remain there? So if you hit it with the lower energy, then it just bounces back, and in the end the crystal remains as a perfect lattice. But if you hit it harder, then it moves away and creates a permanent lattice defect. And now we assume that this same kind of a threshold gives the threshold for creating the electron-hole pair, which means that this is basically the threshold for having an observable signal or not in this kind of an experiment. Now, maybe I will, since I've already spent quite a lot of time, I will skip some of the maths here, describing how you then compute the event rate for this kind of an event. Anyway, the idea is that now, of course, the event rate depends on the direction, since you have this minimum energy that you need to create the defect, and this is now a function of direction due to the crystal structure. This we have computed for different kind of interactions with the dark matter, and what we then see, for example, for a low mass dark matter particle, these plots now show the event rate in the color code for standard assumptions of the halo model and the dark matter interaction. The blue circle kind of shows the direction where the dark matter particles are coming from throughout the day, and there's a blue dot showing the direction at the moment. So these correspond to 4 different times of day. And you can see that when the direction of the dark matter wind corresponds to this kind of black dot here in the crystal, the black region is the region of low threshold. So here it is easier to excite the signal, so you get a larger event rate there. Whereas when the direction of the wind is coming from this kind of a region where the threshold is higher, then you get less events. And this plot here then shows the variation of the event rate throughout the day due to this effect that the dark matter wind is kind of scanning different regions. So you assume your crystal is a monocrystal oriented in a certain way in the lab frame, and as the lab rotates with the Earth, the dark matter wind is kind of scanning the crystal from different sides, and you see a modulation in the event rate. Now, this effect is only there if the dark matter particle is light. If the dark matter particle is heavier, then you see the events get more and more spread. And here, so this is for 300 MeV particle, this is for a 5 GeV particle, you see the crystal structure is basically already gone from this figure. So only for a narrow range of dark matter masses can you kind of have this effect. But of course, now this range depends on the material. So for a given nuclear mass, you get the given range of dark matter masses that are relevant. And then, of course, you could maybe build experiment with different materials to probe different dark matter masses with this. That's the idea. The structure of this signal also depends on this interaction operator. So now what I showed here was for this simple so-called spin-independent scattering operator, but you can have momentum dependence or velocity dependence in the interaction operator. This is in kind of an effective theory where we just expand the scattering amplitude squared in terms of the just based on the Galilean invariance of this effective theory, there are only a few types of combinations that can appear here. They are the even powers of the momentum transfer Q, and then the even powers of the transverse velocity to the scattering direction, this V perp. So that's why there is this kind of a well-defined basis of operators that can appear. And here we have then checked for a couple of these different operators how does this event rate as a function of the scattering angle look for these different operators. For very small energies, they all look kind of the same, or for very light dark matter, but for heavier, they begin to differ. This plot shows this then the resulting modulation of the event rate for now two different types of operators. So the black one is the one I showed before, and the red one is a different interaction that gives rise for small dark matter mass to a similar modulation, but for heavier dark matter, you see that the structure changes. So presumably, if you're lucky enough and you have an experiment big enough to gather enough data, you could use this effect not only to identify dark matter, but also to identify how it interacts with the nucleus, because you could see the shape of this modulation signal in your event rate, and then that could tell you something about the way that the dark matter particle interacts with the nucleus. All right, here we try to see if you can, using just single material, if you can scan looking at different Fourier modes of this modulation spectrum to see if you can always separate any two models of each other. This is still a bit inconclusive. One needs to do a more proper statistical analysis on this, which is something that we are currently working on, but it looks promising if you have enough data. Okay, I will quickly mention the solar neutrino background. So this was the problem with the neutrino background, which looks like this. So this is the expected recoil spectrum from solar neutrinos. So these are all neutrinos that come from the sun. They come from the different nuclear reactions taking place in the sun, which are the names here. So the sum of these spectra is the total spectrum that then you expect to observe. You can compute the expected event rate from these. And now a nice feature kind of this standard halo model, if this is the correct velocity distribution of dark matter, is that the dark matter particles never come from the direction of the sun. So it just so happens that that our motion in the galaxy is such that looking from the Earth frame, our motion with respect to the galactic crest frame is never such that we would be moving kind of that sun would be directly in between us. So since the neutrinos come from the sun and the dark matter comes from the inverse direction to which we are moving with respect to the galaxy, they always come from different directions. So here again, this plot shows the direction of the dark matter in 3 different times of day, and this plot shows the direction of the neutrino events at those same times. So you can see that they are always kind of centered on different parts of the surface. So if you could reconstruct the direction completely, then you could separate the dark matter and the neutrino events from each other. Now, with this technique that we have, you cannot separate the direction, but you can try to use this modulation amplitude to identify the dark matter. It will have a different phase than the neutrino rate, because the neutrino is scanning a different part of the crystal than the dark matter. Maybe I'll skip this part here. We just discussed the statistical analysis between now separating this daily modulation from the well-known annual modulation effect of dark matter. We found out that both are practically as usable. So you can use either or, but having both the annual modulation and the daily modulation signal, as you do with dark matter, if it has the daily modulation signal, adding the both modulation features doesn't really add extra information to your statistical analysis. So just having one or the other is already good enough. So here it means that basically you can use the daily modulation to double check if you already have a signal with annual modulation. but it doesn't really help in the statistical analysis to separate the signal from the neutrino background more than the annual modulation already does. So this is kind of what this plot shows here. The yellow and the purple line show the kind of reads of the experiment that you can get with either taking into account the daily modulation, or the yellow line shows what you see if you just pin the events per day, so you don't look into the modulation inside the day. And the yellow and the purple lines are almost always on top of each other, so the daily modulation doesn't add as much as you might have expected if you already have the annual modulation. But if you don't have annual modulation, the daily modulation alone gives you practically as much extra gain as the annual modulation does. So this might be useful because, for example, it might be problematic to operate the experiment in stable conditions for a full year. So that's why if you just gather batches of separate days, you can more easily perhaps guarantee a stable operation, and then that signal alone should be as good as the better known annual modulation signal.
And you expect the flux to be large enough to be able to see a daily modulation?
Well, that is of course the main caveat here. So, well, I mean, you really don't. So what is shown here is the size of the experiment that you need if you run it for 1 year. So in order to have a significant improvement over just counting the number of events, you need something like 10 to 3 tons of the target material. And yes, this is not really currently feasible. So yeah, so for this technique, this is kind of in the fantasy world as of yet. But of course, we are hoping to find, we are looking at different materials and trying to see perhaps somewhere this effect is stronger. And so this is more like a proof of principle than an actual proposal for an experiment.
Sorry, Matti, it also depends on where your experiment is on the planet, right? So
the size of the amplitude. It depends a bit on that, but not too much. Yeah, we looked at this a bit, but you can mostly compensate for this by changing the orientation of your crystal. So depending on where you are on Earth, you can just kind of try to orient your crystal in such a way that the modulation is maximized.
Yeah, what I was going to suggest was that would it help if you have kind of different experiments on different parts of the planet too?
I mean, sure, but yeah, I mean, just for this effect, you can do the same by just having 2 crystals with the crystal axis not aligned. So then they should have different phases, and I mean that would be, of course, a good double check if you see the both of the, let's say you have one crystal this way and one crystal oriented in a tilted angle, then you should see the same signal but with a different phase. And if you do, then of course that's quite an unambiguous proof of the source of the signal. This you cannot do with the annual modulation, of course. The phase of the Earth moving around the sun is what it is. So so this you can, so that would be of course an extra benefit of this daily modulation signal.
Absolutely,
if you can achieve it. But yeah, right. Currently, for the neutrino, if the rate is small enough to be kind of comparable to the neutrino interaction rate, then this is very hard. Of course, there still remains, if I just show the plot back with so these numbers that we showed were, of course, if the cross section is here kind of below the neutrino floor. Now, if the dark matter interact, there is still a lot of room here above. So if the dark matter scattering rate happens to be higher than this, then you don't need such many tons of the experiment. Then you just don't worry about the solar neutrino background. But of course, it would still be a nice feature if you would be able to see this daily modulation, because it would kind of be an unambiguous proof that the origin is indeed coming from the galaxy, because the phase was match what we expect. Okay.
May I ask another question?
Sure.
So
yes.
Your technique is also kind of not model independent, but your dark matter doesn't have to be a WIMP, right?
Well, it doesn't have to be a WIMP, but it has to be a particle with a kind of very specific mass. So, so mass in the kind of a GeV, below GeV range. So, yes.
So it would be a thermal dark matter.
Well, I mean, of course, this method doesn't care what was the origin of the dark matter particle in the early universe, but yeah, I mean, the mass has to be kind of in this ballpark where you still can have these thermodynamics. So
okay, thank you.
All right. So my last topic is now discussing a different type of experiment. So the previous, all this modulation was due to the fact that we assume that you either see the signal or not, depending on whether you create the electron-hole pair, which we assume is correlated with this defect creation process in the crystal. Now, there are also these type of experiments that don't apply any voltage over the crystal, but instead just try to monitor the heat deposited to the crystal via, for example, via this kind of a setup where you have the thermal link from, so the crystal is cooled to a millikelvin range temperature, and the thermal link from the crystal to the cryostat, to the heat bath, keeping it in this cold temperature, goes via let's say a gold wire, and then in between you put in a very precise thermometer, this kind of transition edge sensor. So this is a superconducting material that you keep in the temperature just in the transition temperature. So any small change in the temperature of this test will dramatically change the resistance, and this you can observe. So so since the coupling of the thermal coupling of this crystal to the thermal bath goes via this thermometer, this test, then you any scattering event that deposits energy in the crystal, the energy must flow via atomic vibrations, phonons, through your thermometer, and that's where you detect it. So there are different methods for this. This is one possibility of putting it with the wire. Another one is to kind of coat this crystal with these kind of detectors on the surface. So there are different variations of how this method can be used, but the idea indeed is anyway the same, that any motion, thermal motion deposited in the bulk of the crystal can only escape via the surface, via the coupling to the thermal bath, and that coupling you monitor. And that way you can, in principle, measure any energy deposited in this crystal. So now you are no longer limited by seeing an ionization or an excitation of an atom or anything. As long as there is any atomic vibrations, those vibrations must escape via the surface of the crystal. And if you carefully monitor the temperature on the surface, then you can see this in principle. Currently, these limits, there is, of course, I mean, always some instrumental noise when you are monitoring the let's say the voltage over applied this transition edge sensor or whatever you are doing. So of course you cannot see. There is always some lower limit on the energy deposit that you can see, but these are currently the most precise or the lowest energy threshold that have been built, and these are of the order of 10 electron volt with this technique. Now, of course, if you now create a lattice defect, then that defect stores some energy, because of course the perfect lattice is the lowest energy state of the crystal. Now, if some atom moves to a non-perfect lattice site, then its binding energy in that site is smaller than its binding energy in the perfect site. So it means that there is some energy stored in the formation of this defect. And these energies are typically of the order of electron volts or can be tens of electron volts. So they are of the same order as this kind of thresholds that have now been achieved. So now it becomes important that if you measure this heat signal with these very low energies, then you must understand how much energy is actually stored in the crystal in these events, because then that will affect the spectrum that you actually see. so here we have looked at a few different materials that have been used or have been proposed to be used in these kind of experiments. There is what we plot here is the energy stored in the defects as a function of the energy of the recoil event. And this actually also varies a lot depending on the direction of the recoil, but what we saw here is the average over the whole sphere. The red line here is for diamond, then we have silicon and germanium in green and purple, and then blue for sapphire. So these are all elements that have been used in these kind of experiments or proposed. And what we see specifically for diamond is that it has this funny behavior that there is a sharp threshold because the diamond lattice structure is very rigid. Then for recoils below 30 electron volt or so, there is no defect formation. So there's no energy lost. And then very sharply, the amount of energy lost in the recoils rises. Whereas these other materials have kind of a steady slope. So every time you hit it, you on average lose some energy on the recoils. But for diamond, you first don't lose anything, and then you start to lose a lot. And this creates a funny behavior in diamond, where now in this plot, this is from a publication where we don't need to go through every detail of this plot, but I'll just say that the blue lines in this plot show the unmodulated spectrum. So this is just a fit to some data. The data points are from this kind of a prototype experiments. We don't need to worry about what the data means, but just to show the blue line is the unmodulated spectrum that you see, and the orange line is what you should see if you take into account this effect. Now, these data points are from a measurement using sapphire, and indeed we see that for sapphire, the blue line and the orange line are on top of each other, more or less. So this is because in sapphire, you don't get much energy loss, and the amount that you get is kind of a steady slope. So this doesn't modulate the observed recoil spectrum a lot. But in diamond, for some energies, you start to move the events effectively towards lower energy. So that's why here at lower energy, you have kind of an excess over what you would see otherwise, and then you have a deficit above, because the events effectively from these energies have been moved to the lower energies because some of the energy was stored in the crystal and not recorded by your experiment. So this kind of a experiment on diamond has not been performed yet, but this is what we kind of propose here, that you can use a diamond detector, let's say on side of a sapphire detector, to see whether the spectra in these two experiments differ like this, that in sapphire you see a smooth function, but in a diamond you should see a bump and a dip. Here we saw what you expect for dark matter, and this looks specifically dramatic. So this is for 1 GeV dark matter particle, again in the same four materials, diamond, sapphire, germanium, silicon. You see that in diamond, you expect to see this kind of a very sharp peak in the energy spectrum due to this effect, whereas in sapphire, for example, the spectrum is more smooth. So this is an idea that you could, first of all, that you have to take into account if you want to very carefully calibrate your solid state experiments to understand that what you're reading actually tells you about the underlying recoil event. You must understand that some of the energy might be stored in the lattice defects. But perhaps more interestingly, since this depends so much on the material, you can use experiments with different materials to confirm that the events indeed are from nuclear recoils, because then in the different materials from the same source, you should see very different spectrum, because the spectrum in diamond is modulated a lot compared to, for example, the spectrum in sapphire. And then I come to my conclusions. Yeah, this took longer than I expected, but okay. So the idea is that for low threshold solid state detectors, the lattice defects become important because your recoil energies that you are observing start to be of the same order as the typical energies that are required to create these defects or that are stored in the defects. This can affect the event rate that you observe, and the direction dependence can give you a modulation signal that you could hopefully observe, although this might require very, very large experiments indeed that are not yet feasible. And in these kind of calorimetric detectors, you could perhaps use this modulation of the recoil spectrum to confirm that the events indeed are from nuclear recoils and not, for example, electron recoils. That should not give rise to lattice defects. Okay, so that is my last slide, and I thank you for the attention.
Thank you, Matthew.
Thank you very much.
Yeah, so I have a question if nobody else wants to jump in. So on this previous slide with the annual modulation, what is the size of the diamond you would need? I mean, is it worth it making an experiment with the diamond?
So for this experiment, yeah, so here we haven't really looked yet into, I mean, this you should in principle see, since this this effect, you don't care about the timing. So these plots are for if you average over the direction. So this basically assumes that you sum over the events in your data collecting period. So that's why to see this effect, you don't necessarily need as much exposure as you need to see the daily modulation, which indeed for daily modulation, you need a lot of events because you need to populate kind of every time bin to be able to see something. Whereas for this effect, you don't need to care about the timing because this effect just shifts the event from higher energy to lower energy. Now, there is some dependence on the direction in this effect as well, of course, because this defect creation process depends on the direction. But we are not yet completely finished with this analysis, but what we looked at is that kind of this relative effect remains the same more or less throughout the day. So so here in this, to see this effect, you don't really need to care so much about the timing of the events, and therefore you don't need so much exposure necessarily. Currently, what is technologically feasible is something like a gram scale diamonds. So certainly you cannot make a ton scale diamond detector, but you can make a few grams.
I don't think we even have a ton of diamonds on Earth.
Yes, I mean, I think these are industrial diamonds. I guess you grow it in a lab. You don't go digging for it.
He wants to collect jewelry.
Yeah, I guess, I mean, sapphire is not that much cheaper. I don't know.
Yeah, I don't know. I mean, I guess sapphire is also industrially produced, so it's probably cheaper than diamond, but I don't know if there is a relative difference. But yes, certainly, I mean, this kind of both sapphire and diamond are you cannot make them in bulk, whereas germanium crystals, of course, you can make in bulk.
Yeah.
So there is probably no problem building like a kilogram-sized germanium crystal.
I see. And when you build them or when you grow them, you get less defects, right? You have more control over it.
Exactly, that's the idea, that you want to grow them so that they are monocrystals, so that the lattice structure, when you begin your experiments, is as close to a perfect lattice as possible, right? That's important, that you also need to know, especially for the daily modulation effect, you need to know precisely the crystal orientation. So it has to be a monocrystal and a grown in the lab. Yes.
So how difficult is that to do, to grow a monocrystal of a kilogram of germanium?
I don't know much of the details of this, but I know that these kind of germanium crystals have been, well, probably not kilogram scale, but at least a scale of 100 of grams or so. These have already been used in the what's called the CDMS experiment. So these do exist. I guess the problem, if you try to increase the size a lot of the crystal, then the problem becomes also to the kind of this instrumentation. I mean, you won't need to keep it cool in the cryostat, and you need to have this this thermal link that you can monitor. Now, if the kind of the thermal capacity of your crystal becomes very, very large, if it's very large, then I guess you will probably have some problems with just collecting all the phonons from the very large crystal. So it's probably a better idea to build many small crystals.
ones, yeah, right, okay. Yeah.
And how close are these ideas to being implemented in experiments?
Well, yeah, so prototypes exist with sapphire and germanium and silicon. These have been done. With diamond, I think these are kind of currently in the stage of just being prototyped. So I don't think there is any run with any actual data from diamond detectors yet, but those are being experimented with.
So we need to go through our grandmother's jewelry.
Yes, yes. Although I indeed think that old jewelry might be that the crystal is no longer very perfect. If it has been like hit with something, then you might get cracks and so on the crystal. So might be better to grow new ones.
Mm-hmm. I have another question, a silly question. So Xenon N-ton is taking data. Do you know what is N? I'm guessing it's just 2 at the moment, right?
I don't remember exactly what is the target mass of Xenon N-ton. I somehow, I think it's something between 2 and 3 tons.
Oh, wow. Okay.
But I'm not completely sure.
Mm-hmm.
Yes. So it is improvement by a factor of few to, or maybe even like a factor of 2 to the previous one. So it's not that big of a difference.
Yeah. And then, so if you go back to the direct detection cross-section plot with all the different experiments on it.
The limits.
Yeah.
This one.
This one, yeah. So in the region that your technique would solve is the low mass region.
Yeah, kind of this region, and actually even, so this is cut off at 1 GeV. So actually we are mostly interested in kind of this region around 1 GeV and down to, let's say, 0.1 GeV. So.
Yeah, but currently the limit that we have is basically because of the techniques we're using, right?
Yes, this kind of the reason why these all burn up is because they all have a low energy threshold that is large enough that you cannot really see dark matter particles below a few GeV mass here.
Yeah.
So, for example, this crest is using this kind of detector of the similar type as the one that I was discussing last, that measures directly the temperature of the crystal. So that's why it can extend to lower energy, lower dark matter masses. But it's a very small experiment still, so that's why it's the limit is not as strict as the ones that use much larger target masses.
Yeah.
And is there any natural reason for the coincidence of that transition in the neutrino floor and these ones?
No, I don't think
just
so.
An accident.
So this just comes from the spectrum of the events that come from the. So this basically the neutrino floor contains 2 components. So this bump here is the solar neutrinos, and then this line here is from the kind of cosmic rays that hit the atmosphere, and then you create neutrinos in the atmosphere. So so the reason that the solar neutrino flux ends here, and it just happens to coincide with the mass range that I don't think there is any kind of natural cause for those numbers to be the same.
It's not because detectors are after evolving from neutrino detectors?
I don't think so. No, I don't think so. It's just it has to do with the mass of the particle of the target nucleus, and then it with whatever the kind of the detection capabilities are of those experiments. So I don't think there is really any connection there.
Okay.
Yeah, I guess most people have left. That was a very good talk, Matti.
Thank you.
Thank you so much.
It took a bit longer than I expected, but
good. Well, it took a lot less longer than I was expecting. So, but I always learn something new when I talk to you. So this was fantastic. And
thank you very much. I'm going to stop the recording.
Yeah,
that's okay.